Good day. My name is Shilvio D. Linton. I'm a student at Iowa State University, and I currently study soil science / GIS, which is soil informatics. That's what we're going with. So today I'm going to just ask and answer a couple of questions regarding best management practices. So I guess I'll start by defining what best management practices are. They're essentially things that a grower can do to reduce soil erosion or increase their soil quality or soil health. These things are pretty useful since soil is a finite resource. Yes, soil is always being made. It's extremely slow, and it's also being lost. In what we may consider native conditions, soil isn't lost very rapidly. However, when it comes to agriculture or anything that induces land cover change or land use change, we get a reduction in the amount of soil that stays on the field or in a given area. That doesn't mean it's all being lost. So if we have soil erosion, that doesn't mean everything that starts out on the field and is picked up leaves the field completely. What we mean to say is that it's not in the original location. So yes, it can move slightly uphill. More of it does move downhill, but it doesn't mean it's taken off of the field entirely. So I'll start with the first question. Someone's asking to describe methods for controlling soil erosion, particularly residue management and contouring. So there are many management practices, and I'll start by answering the residue management. So residue essentially can leave a layer of material that can absorb the impacts from raindrops. So a raindrop falls, it splashes soil, it can detach, and when it's detached from the matrix or the set of soil, then it can move downstream. What residue does is essentially get in the way of that. So a raindrop falls, hits the residue instead, and with a larger surface area, it diffuses some of that energy. Another thing that residue can do and does do, it does depend of course, is create a degree of roughness. So when water is running down a hill or down a slope, it has to travel around the residue or over the residue. To go around it or to go over it requires energy. If you have a longer path to take over a particular slope, you're going to have to use some energy to get over that. And the steepness of that slope also decreases. So residue can definitely do a decent job. And studies have shown that leaving crop residue on, particularly around 60% is preferred. It has significant impacts, and it takes, I guess it's the most bang for your buck, essentially. The next one I'll talk about is contouring. So contouring takes that concept of routing water along the paths and making the slope up from the source to wherever it's heading longer, but taking the most optimized route. So contouring essentially says, make your plow lines according to the contours. So if you've ever seen a contour map, they're equal intervals of distance in elevation. So a single line, an iso line, would say, we're 20 meters above the surface. And an entire line of these 20 meter above the surface points would be your contour. So contouring says, let's plant along this direction of this 20 meter, hypothetically 20 meter line. That's, I think it's pretty good, right? So you reduce the net slope of the field. So water that's traveling has to go a long way to get down. And it also keeps the soil within a particular level or height or elevation, such that, you know, it's not running down and piling up in these particular areas. Well, of course, along the contour, you will have some deposition. However, it's not as bad as, say, leaving it for an entire, you know, 60, 100 meters before it starts settling out. That that's a little bit more risky, right? The limitations to contouring, and I'll mention it later on in some others, is that when you have a particular contour, you still want to keep your machinery running through it, right? You don't want to have to take extra trips, because extra trips is extra gas, that's extra money. We don't want to be spending that extra money. So if you have a machine that is hypothetically 30 meters wide, you don't want to have your contours 50 meters apart. So you'll be running that extra trip and covering a piece of land you've already covered. And that extra land is money spent. The next one that I'll tackle is strip cropping. So strip cropping is essentially planting in specific rows which have a grade to them. They have some height to it. And what this does, it reduces erosion from water transport and also some wind erosion. The idea is that you want to protect your crops or your seedlings from that incoming harsh wind when they're still kind of weak and susceptible. How it works, check. Guidelines for using it. So interestingly, I mean, it sounds like a really great idea. However, if you are traveling in the same places year after year after year, you might run down your, like, the little area that you're in. And if you're planting in a particular areas, you're developing soil in one area and leaving the other susceptible. So I'm starting to get at preferential flow. So water is going to end up carving its little path out where it wants to travel. Now that can be good, it can be bad. If it's a good flow path and you can take care of the sediments that are leaving aren't terrible, you're applying your fertilizers where the plants need it, you're doing selective weeding, so you're weeding in the inter rows, perfect. But you also are going to want to have some vegetative cover as well. So forages or other crops, which will, you know, take at least 50% of the rotation, and they can resist the trampling or your vehicle driving over them. So essentially, leaving any area fallow is begging for some soil erosion. The next thing that I'm going to focus on is terraces. So terraces were like my very favorite management practice. Waterway, which we will get to in another video. But terraces are essentially a structure that breaks up your hill. We're not like chopping a hill in half, but we're doing that. So in the calculation, we are effectively reducing the slope. The slope length, sorry. So if you have a long slope and you've got water running down, say 200 meters, by the time it goes down 100 meters, 150, 200 meters, its kinetic energy is ridiculously high. For all the vertical travel it makes, it's going to pick up kinetic energy. The potential at the top turns into kinetic wherever you're measuring it. Of course, there are losses from friction and roughness and routing. It's not a perfectly straight line, but for all intents and purposes, you don't want a really long slope. around this, you can terrace. Terrace effectively breaks that hill, that slope, into whatever section that the terrace is located at. So your terrace is going to stop the water, stop the flow, and divert it safely along a partial contour. If you have it directly perpendicular, you can get some, if the water has enough energy, it can just break it. You'll have wasted a lot of time and money installing it. So you use a partial contour to make sure that when the water gets down, it's eased into its next path and it loses some energy by hitting up against the side. That's essentially how terraces work. They have the same limitation that strip cropping does. So you want to make sure your terrace spacing is wide enough such that the operator can make an even number of trips between the terraces. If he has to make more trips to cover the same amount of land proportionally, again, we've wasted some monies. And who likes wasting money? No one. All right, so the next thing I'll tackle is the all-famous USLE, or Universal Soil Loss Equation. The Universal Soil Loss Equation was, it's an empirically derived equation for predicting soil loss, or loss in weighted sediments per year. It's originally built for entire watersheds, so it should be applied, sorry, for entire watersheds because it's quite general and makes huge generalizations. However, it was constructed on these unit plots, I believe 22 meters by 8 meters, something to that effect. I'll have a correction in the description if I turn out to be wrong. I'm doing this off the top of my head here. So Universal Soil Loss Equation has a couple of physical and situational variables, and you essentially multiply them all together and calculate whatever amount of sediment losing or soil you're losing per year. So there are a couple of variables that go into this. I'll start off with A. A is your soil loss, sediment loss per year. So it's the units would be tons per acre per year. So how many tons of soil is each acre losing per year? So imagine a very slim amount of soil loss from every single part of the soil. That's what the measure is taking. Of course, a field isn't just 1 acre. A field can be 12 acres. A field can be, or a field, watershed area can be 12 acres. It could be 15 acres. It could be 30 acres. And depending on where you are, depending on your field size, then we're going to have to take that into consideration. So the next one, so A, the loss, is equal to R times K times C times P times LS. I'll start with LS because it's kind of weird. So LS is the length slope factor. So we said earlier with the terraces, the idea is we're going to break up the length of our hill or our field, because if you have a longer continuous face, then you're going to end up losing a lot more. You've got a lot more energy because it doesn't have to slow down or stop. It can just keep going unimpeded. So slope are interconnected, as you can imagine. If you have a steep slope, you have more runoff potential. If you have a longer slope, you have more runoff potential. They aren't related linearly, so that's why they're normally kept together. If you have a very steep slope we're saying like 40 slope, I mean, you don't have to have a very long slope to get the same effect. So you can have 100-meter slope, 100-foot slope, 100-meter slope, and have, I don't know, you can have 100 meters and a 10% slope and have significantly less runoff than, 500 meters at 10% slope and have significant amount of runoff or less runoff than a 100-meter slope that has 40% slope. Ooh, I hope that wasn't really confusing. I also hope you get the idea though. The second factor, I mean, yeah, sorry, if you don't really understand that, I suggest quickly looking up USLE and you'll see what I'm talking about. The slope length steepness factor, you'll see the tables for it, or a chart just depicting what I'm describing. The second one is rainfall. So rainfall is for rainfall intensity. It depends on how close are you to water. It also depends on how, what's the relative elevation in that area. It definitely varies. If you are closer to mountains, that's under a rain shadow, of course you've got less. So the R factor tries to account for. The K factor is soil erodibility. It assumes 2% organic matter. That's something to just throw out there. And it considers sand, silt, and clay. So sand doesn't have much internal cohesion. Silt, so-so, but you can lose a lot of silt. It's large enough to not have a cohesion, but small enough to be picked up and carried away pretty easily. And clays have a lot of cohesion due to their extremely high surface area, net negative charge. So they are going to stick together, and those are mostly resistant. It's all modified, of course, by the soil structure. If you have very fine or granular, if you have fine granular, blocky, platy, or massive structures, of course, you're going to have a different K factor. The last two, C and P, are your cropping system and management practices that you apply to whatever field or hill that you're tending to. So C, your cropping system, is essentially, what are you planting? Am I planting corn? Am I planting soy? Am I planting alfalfa? If you have a particular cycle or particular system, such as corn, soy, we just call that CS, then you have a different C value. If you are doing continuous corn, you have a different C value. If you have continuous soy, you have a different C value. And these are on massive tables, so you can go check them out and plug them in. There are a couple things that are also there. We have like forest, if you're in permanent forest or permanent pasture, or if you use a management intensive, rotational grazing, then that also can be categorized and factored into your universal soil loss equation estimate. So for example, I'm going to give you some of these values. If you just have bare soil, your value is 1. That means whatever the environment suggests, you're going to get it. There's no modification. If you have ridge-tilled corn soy rotation, your value is 0.1. So there's an order of magnitude difference. If you have a 1/6 rotation of corn to grazing to yeah, sorry, corn to small grain to meadow for like foraging for 4 years, then your value is 0.011. If you're in strictly pasture, 0.005. So you can see the scale that your cropping sequence really has. And permanent forest is 0.005, right? So the last part is P. So whatever practices you're applying, like the ones we talked about earlier, strip cropping, contouring, terraces, also including grass waterways, chisel till, no till, I think I mentioned that, reduced tillage, all of those have effective P or practice values. And these coefficient was added on a little bit later and continued to be modified. So the limitations, well, those are all the values for calculating your soil loss in the universal soil loss equation. So I'll go over them one more time. You have R, the rainfall erosivity factor, S, slope, L, length, which is slope length, the K, soil erodibility, C, your cropping system, and P, whatever management practice you have applied. You multiply those all together and you get the A, soil loss or sediment loss in tons per acre per year. Of course, you can calculate this in hectares, but I suggest, or hectares, I'm sorry, and you can suggest that, I would suggest doing that afterwards, as doing all the individual changes, it's a little bit challenging. You want to apply this to an international forum, you want to switch to hectares, because the rest of the world uses it. Get on in America. So the limitations to the universal soil loss equation is that essentially it suggests that when you have whatever situation, if I have a terrace and I have these particular soils in these particular areas over my entire field, I'm going to get, say, 30 tons per acre per year. That's not necessarily true, right? So in the beginning, we mentioned that you can have erosion occurring and also have deposition later on, right? Before you leave the field, you can have deposition. And so the amount of sediments, the water, the rainfall, or the irrigation water, or whatever is running off your field can have, it has a maximum carrying capacity, right? So once it reaches halfway down the hill, if it's hit its capacity to carry, then it's not going to carry anymore. If it gets into an area where it loses capacity to carry, it's going to deposit sediments. So everything that is picked up here is not delivered. So you can have overestimations. You can also have underestimations. The K factor, for example, isn't as static as it's suggested in the US soil survey or any other soil survey you're using. Soil properties do change over time. If you have an accumulation of clays because you're at the bottom of a Katina, you're definitely going to have a little bit less erosion there. If you are going over a part of land that happens to have a little bit more stubble to it, if it has microtopography, it's going to change the erosivity, well, because you're slowing down the water. The soil itself has a degree of control. So you have to take the universal soil loss estimates with a grain of salt. So I've got two more things. What are the sources and transport mechanisms of nitrogen and phosphorus to water bodies? So actually, this is a really interesting thing that I will be researching pretty soon, or adding to the body of research that already exists. There are a couple mechanisms specifically for overland flow, and then there's some for groundwater flow. So overland flow, of course, you can have nitrogen that is lost as nitrate. Same thing for groundwater. And it runs through your soil, down the hydrologic gradient, and exits your field. It's kind of hard to do anything about this. So the transport mechanism is quite simple. Nitrate, water, leaves the field. Phosphorus, on the other hand, most of the phosphorus that leaves your field is leaving bound sediments. So wherever you have soil loss, you are probably having phosphorus loss. Any sediments that leave your field, anything that's delivered outside of your watershed, outside of your field, is going to be pretty relatable to a significant phosphorus loss. Now, it's possible to have dissolved phosphorus, leaving, say, a tie line with other groundwater flows, but it's not as significant as nitrogen's loss from that same way. So the last thing we'll talk about are reservoirs or storage. So if you are to put in a basin or like a little pond, you have to design it in order to accommodate whatever the upland contributing area is going to give, whatever uses you want to get out of it. So number one is sediment storage, right? So you have soil loss from your field because you're doing something to it. Even if you're not doing anything to it, say it's still in prairie or some natural state, let's say it's in, permanent forest, you're still going to get a little bit of sediments. So if your intent is to capture whatever water for some purpose, you have to make room for whatever sediments are going to leave per year, and then also consider how long do you want to leave this such that you don't have to do active maintenance. So you don't want to be, dredging your little pond every 2 months. That would be miserable, right? So you have to consider how much water is coming in and also how much space the sediments are taking up. The second part is useful water. So useful water is, just as it suggests, useful. So if you want to have a particular use for collecting that water, let's say we're going to make a little pond for fishing. We're going to use this water for cooling down a generator. We're going to water livestock, or we're going to supply some irrigation. You want to make sure you have enough water in the pond, right? If your pond fills up and flows out, and you're like, oh no, all the water, right? You want to design such that the maximum amount that you want to have is going to be present when you need it. And of course, this all has to consider the upland area, right? So if you are in a really rainy area and you have a small field, you really have to consider you probably aren't going to get a ton of water for irrigation just for the fact that your field is small. So the area that is feeding this pond is, not sized well enough. On the other hand, if you have a really large area but you barely get any water, barely any precipitation, you're going to consider, well, if rain is coming down, you're probably going to get more infiltration, less runoff, and I might not be able to fill my pond. So the last thing to consider for designing this pond is flood storage. So say you size everything nicely, but then you get a storm. Sunny storm, you're getting a 50-year storm or a 75-year storm. That means a storm that has a probability of occurring only once every 75 years, once every 50 years. That storm really put a lot of stress on your little pond or embankment. So you need to design to have adequate space to store some of that, and then on an adequate structure for getting rid of the unnecessary water. So you would have to determine how much that is, calculated in volume, how much water you want to have over the course of the year, calculate that in volume, and then the estimated storage for sediments, calculate that in volume. And once you have all three of those, add it together, and that's the area you need. And there are some GIS packages. So GIS is Geographic Information Systems. So there are some GIS packages that can size or locate a pond for you. However, I would probably go to a consulting firm since they have experience and they know a couple more nuances that machines and the person that might be planning it might not know. Got an ag engineering background. I'm convinced you might have learned a little bit of this before, and maybe a package is okay. Again, if you wanted to get something in CRP or a government program for helping you fund this, you probably will have to go through a certified engineer to have the yes stamp of approval that this was done well and properly, and to standard. So those were a couple of things that popped up in my studies. If you've got questions, leave a comment in the low comment section. I was going to say low bar. The low bar's for me. And thank you. Have a great day.